All right, chapter 13, acids and bases. You made it through chapter 11, kinetics. You've made it through chapter 12, equilibrium. Now we're going to take a little bit of a break, hopefully something that's a little bit more familiar and a little bit more approachable, a little bit more conceptual, and that's acids and bases. And most people have probably come across the terms acids and bases before, so hopefully we're going to have a good chapter. So chapter 13.1 is going to be the natures of acids and bases. Then we're going to talk about acid strength in 13.2. 13.3, we'll look at the pH scale. We're going to do a bunch of stuff with pH scale. Don't worry, not frightening. Calculating the pH of strong acid solutions, very easy. Calculating the pH of weak acid solutions, a little bit trickier, but not bad. Bases, and then polyprotic acids. 13.8, we're going to look at acid-base properties of salts. 13.9, we'll look at the effect of structure on acids and bases. And then 13.10, acid-base properties of oxides. 13.11, the Lewis acid-base model. And 13.12, a strategy for solving acid-base problems. Just a summary for those. All right, so let's look at some general properties of acids. All right, so acids tend to have a sour taste. And so the word oxygen in German is sour stuff, and it means acidic. So something like malic acid, that's the acid on Sour Patch Kids. They have the ability to dissolve lots of metals. They have the ability to neutralize bases, and they change blue litmus paper to red. And so here are some, the HCl is what we call a strong acid, and you'll notice it has this H in it. And acetic acid is a weak acid. You'll notice that it has this H over here on what's called a carboxylic acid group. So that's this structure here. And what we're going to see is that this proton is able to leave and go out into solution. So here are some common acids. Hydrochloric acid, it's used for metal cleaning. It's also called muriatic acid. Sulfuric acid, the most common industrial chemical in the world. It's used in fertilizers and explosives manufacturing, dye, glue production, automobile batteries, electroplating copper. Nitric acid, which is a reducing acid, so it's going to undergo some electrochemistry. Used in fertilizers, explosives manufacturing, dye, glue production. Acetic acid, we recognize this guy, that's what's in vinegar. It's a plastic and rubber manufacturing ingredient. It's used in food preservatives. It's the active component of vinegar. Citric acid is present in citrus fruits, such as lemons and limes, and it's used to adjust the pH in foods and beverages. So you'll see lots of citric acid in food. These guys here are all weak acids. Right? And these guys up here are all what we call strong acids. Carbonic acid is found in carbonated beverages due to the reaction of carbon dioxide and water. It's the one that you have to worry about when you're talking about increased CO2 production, changing the acidity level of the oceans and bleaching out coral reefs, and that's from carbonic acid. Carbonic acid is also what's used to buffer your bloodstream to a particular pH so that your physiological pH is maintained where it needs to be. Hydrofluoric acid, HF, this is actually nasty stuff. They have to have special rules for treating and dealing with hydrofluoric acid. It's used in metal cleaning, glass frosting, and etching. It will kill you painfully and slowly, so we want to avoid using hydrofluoric acid where we can. It's also a weak acid, but the chemistry for hydrofluoric acid being a weak acid is how fluoridated toothpaste works and why your toothpaste has some fluoride in it to help prevent tooth decay. And then phosphoric acid is used in fertilizing, manufacturing, biological buffering. So if you want to get some phosphorus into your fertilizer, that's one way to do it. It's also a preservative in beverages. And if you see that experiment where they take a tooth and they put it in some Coca-Cola and the tooth dissolves, it's probably the phosphoric and the carbonic acid that are the ones that are actually doing that rather than the sugar. All right, so let's take a look at this COOH group. It shows up a lot of places. This is what we call the carboxylic acid group. It's a carbon bonded to two oxygens and then a hydrogen stuck on the end. And only the H in this carboxylic group is acidic. So this little H here is able to move and go out into solution. So citric acid, malic acid coming from apples, from the Latin word malus, meaning hand. So malic acid is the one that is in a lot of food sweeteners or food souring agents. Bases, on the other hand, taste bitter. Another word for basic is alkali, and so alkaloids are plant products that are alkaline. They're often poisonous, so your body has evolved to recognize alkaloids as tasting bad or yucky. And that's because you don't want to die after eating an alkaloid. They often feel slippery to the touch for a couple of reasons. One being you're going to start to form soap with the oils on your hands and fingers, so they're going to start to form a little bit of soapiness. That's how you make soap, is you react fat with some hydroxide to saponify it. Saponify means to turn into a soap. They have the ability to neutralize acids, and they're going to change red litmus paper blue. So as much as I can, I am going to try to color code acids as red and bases as blue. Let's look at some of our common bases here. We've got sodium hydroxide, NaOH, where that hydroxide is the base part. Used in petroleum processing, soap, plastic manufacturing. The common name for this is lye, so you will sometimes see the term lye lying around. You can use it in pretzel making, right? That's the food part. Potassium hydroxide, KOH, is used in cotton processing, electroprocessing, soap production, batteries. These guys are strong bases. Right? And what we're going to see with all of these guys, these are all what we call weak bases. So sodium bicarbonate is an antacid. It's the active ingredient in baking soda, and it's a good source of CO2. So you take baking soda and you react it with vinegar, which is an acid. Acetic acid and vinegar is going to generate CO2. That's how you do that, like classic grade school volcano, where you like take the two things, you mix them together, add a little bit of red food coloring. Sodium carbonate is used in glass and soap manufacturing. It's a general cleanser or a water softener. And ammonia, NH3, is used in detergents, fertilizers, explosive manufacturing, and synthetic fibers. It's also used in food production as a way to sanitize things. So if you go into industry, you'll oftentimes want to be ammonia certified. So let's look at some models of our acids and bases. There's three models that we're going to work with, and they're going to go from most specific to the most general. So anything that is a Bronsted-Lowry acid is also going to be a Lewis acid. Anything that's an Arrhenius is also going to be a Bronsted-Lowry, which is also going to be a Lewis. So our Arrhenius is the most narrow definition, but it's also the one that people are probably the most familiar with. And it says that acids are going to produce hydrogen ions in aqueous solutions, and bases produce hydroxide ions. So you got H plus for an acid and OH minus for bases. It's most limited because it only applies to aqueous solutions, right? And it really only allows for one kind of base. That's the hydroxide ion. The Bronsted-Lowry model is going to take things from the proton's perspective. And it says that an acid is a proton donor and a base is a proton acceptor. And so that's a little bit more general of a definition. So you can see where here you've got something that's an H plus donor. Well, it's going to generate H plus. Right? And hydroxide, OH minus, is going to react with H plus to give you water. So OH minus is a proton acceptor, but other things can accept protons, like ammonia, and H3 can pick up a proton to become ammonium, NH4 plus. So our ammonia is acting like a base. And the Lewis model is the most general of all, and it says that an acid is an electron acceptor, whereas a base is an electron donor. Right? And so now you're looking at things from an electron's point of view. And that's the most generalizable, and it works in things that are not aqueous solutions. So if you do organic chemistry, you're going to undergo some acid-base chemistry doing organic chemistry, but it's not going to be in an aqueous solvent. It'll be in something like hexane or chloroform or some other non-aqueous, non-water containing solvent where you're not going to have hydroxide ions or you're not going to have protons necessarily floating around. Right? So let's take a look at these. Our H plus ions, or protons, are produced by the acid, are so reactive that they can't actually exist in water. We're going to say H plus. right? Just because it's easier for us to write it out rather than H3O plus. Right? So instead, they're going to react with water molecules to produce complex ions, mainly the hydronium ion. So hydronium is H3O plus. If you take an H plus and you stick it onto some water, you're going to end up with H3O plus, and that's what the Lewis structure for this looks like. If we go over to the Vesper structure, right, we had water, which was a bent molecule with a tetrahedral electron domain geometry. We pick up that proton. Now, instead of being bent, it's going to be a trigonal pyramidal structure for its molecular geometry, and it's still going to be a tetrahedral electron domain geometry. And even that is still a little bit of a lie, in that this H plus over here, this hydronium ion, doesn't actually exist. It exists in two more complicated forms where you're taking two water molecules and they're basically playing hot potato with that extra proton, right? Because it's hard to shove that extra proton on there. All right, but let's take a look and see what happens when we've got a reaction between HCl and water. So when hydrochloric acid dissolves in water, a proton is transferred from the HCl molecule to the water molecule to form the hydronium ion. So you've got OH, so H2O, and you're going to react it with HCl. And our little friend proton over here is going to hop on over to the oxygen and you're going to form H3O plus and Cl minus. The general reaction that occurs when an acid is dissolved in water can best be represented as follows. So you've got HA, where this A is the remaining part of the acid, reacting with water to form H3O and A minus. This is what we call the conjugate base. Right? So I'm going to form a conjugate acid, H3O plus, and a conjugate base, A minus. Okay? And that's just our generic form. So we're going to see some HA and A minus things going around, where this A is just like, what's the other stuff? And the conjugate base for HCl would have been Cl minus. If it was acetic acid, it would be acetate as the conjugate base. So it's whatever is left over is the conjugate base. So our conjugate base is everything that remains of the acid molecule after the proton is lost. The conjugate acid is formed when the proton is transferred to the base. And we have what's called a conjugate acid-base pair, which consists of two substances related to each other by the donation or accepting of a single proton. All right, let's test ourselves. So which of the following pairs of species are conjugate pairs? A, H3PO4 and PO43 minus, B, NH4 plus and NH2 minus, C, OH minus and H2O, and D, HCl and H3O plus. Pause, give yourself a second. All right, let's come back at it. All right, it's not A. All right, this guy over here is phosphoric acid, and this guy over here is phosphate. But they're not going to be conjugate pairs because we've got this H2PO4 form, which is going to have a -1, and we've got an HPO4 2- form. This would be the conjugate base for this guy, and this would be the conjugate acid for my phosphate, right? So we can only go one proton at a time. Same reasoning here with our ammonium. And this guy, which was, I don't know, ammoniide, right? You would need to go NH4 plus back and forth with NH3. Right, so this guy's out. OH and H2O, that is a conjugate acid-base pair, right? So you're going one proton at a time from a base to something that would be the conjugate acid, right? It's picking up a proton. So H2O is the conjugate acid of hydroxide. HCl and H3O plus, right? These are both acids, right? And you can think of this as being the conjugate acid from the HCl. All right, so your best answer here is going to be C. Right? So let's look at an equilibrium expression from this. You guys should be hot off at chapter 12, used to writing K as products over reactants. Here I've got a reaction where I've got HA, and that's our generic acid, and it's reacting with some water. to form some hydronium and the conjugate base, A minus. In our equilibrium expression, we're not going to include this water, so it's just going to be products, the H3O plus times the A minus over the HA, and oftentimes we'll simplify that and just write H plus and A minus over HA. And we've got some sort of K value with that. We're just going to give it this little subscript Ka to indicate that it's an acid dissociation constant. Nothing special about this. You've done products over reactants for a whole chapter. We're going to see a lot of Kas. They're all going to follow this same form, so a Ka is just a special class of a regular equilibrium constant. Right? And it says what's going to happen when you remove a proton to form the conjugate base. Right? So let's look at an example for acid-base dissociation, sometimes called ionization reactions. We're going to write the simple dissociation ionization reaction, omitting water for each of the following acids: hydrochloric, acetic, ammonium, aniline, and hydrated aluminum 3-ion. Right? So for our first one, HCl is going to react, and it's a strong acid, so we're just going to form H plus and Cl minus. Right? We're going to have our conjugate acid and our conjugate base, right? Where we have H and A. Right? Here we've got our H, and then this whole thing here is going to be our conjugate base part. So we're going to split that up into H plus and our conjugate base, C2H3O2 minus. For our ammonium, right, this guy is going to dissociate one of these protons over here, and it's going to give us our conjugate acid and our conjugate base. Right, so we're going from ammonium to ammonia here. And for this one, we've got another NH3 plus group at the end. We're going to take off one of our H pluses. We're going to leave two H's over here. Right, this guy's going to carry the charge with it, so you notice that our charge is conserved. Right. E, although the formula looks complicated, writing in a reaction is simple if you concentrate on the meaning of what K is. By removing a proton, which can only come from one of the water molecules, that leaves behind one OH minus and 5 H2O molecules attached to the aluminum ion, our reaction is going to be Al, and then in parentheses, H2O6, because it's this hexahydrate 3 plus. We're going to take off one of these protons. Right? This is the conjugate base part. There's our conjugate acid, and all of our other 5 waters stay the same. So our Bronsted-Lowry model can be extended to reactions that occur in the gas phase. For example, if we consider the reaction between gaseous hydrogen chloride and ammonium, so we'll have NH3, ammonia, and HCl gas, giving us ammonium chloride, NH4Cl solid. A proton is donated by the hydrogen chloride to the ammonia.